Since the dawn of humanity, we've gazed at the universe with wonder, seeking answers in the stars, trying to grasp the nature of reality itself. But what if the universe's greatest secrets aren't hidden within distant galaxies? What if they're woven into the very fabric of existence, concealed by our limited perception? We experience the world as a collection of solid objects moving through space and time, yet this familiar reality might be a grand illusion, a simplified version of a far stranger and more complex truth. What if instead of matter, information is the fundamental building block of the universe? And what if the laws of physics are simply the rules governing this information? This is where our journey begins. A journey to explore the mind-boggling idea that the universe isn't just governed by information, but might actually be a colossal quantum computer. To grasp this extraordinary concept, we need to delve into the strange and counterintuitive world of quantum mechanics. This realm, operating at the smallest scales of existence, challenges our everyday understanding of reality. Here, particles don't behave like tiny billiard balls. Instead, they exist in a blurry haze of probabilities, occupying multiple states at once. Even more bizarre is the phenomenon of quantum entanglement. Two entangled particles, no matter how far apart, are linked in a way that defies classical physics. Change the state of one, and the other changes instantaneously, as if they were communicating faster than the speed of light. This spooky action at a distance, as Einstein called it, hints at a deeper interconnectedness in the universe, a realm where information seems to transcend the limitations of space and time. Quantum mechanics tells us that the act of observation, of measuring a quantum system, fundamentally alters its state. This suggests that information isn't just a passive observer in the universe, but an active participant shaping the very fabric of reality. Imagine scaling up these mind-bending quantum phenomena to the level of the entire universe. What if the universe is a vast interconnected network, exchanging information through quantum entanglement? This is the essence of the cosmic computer hypothesis. Just as a computer processes information using bits, the universe might employ quantum bits or qubits. These qubits give the universe an incredible capacity for information storage and processing. This leads us to the holographic principle, another mind-bending concept suggesting that our three-dimensional reality might be an illusion, a projection of information encoded on a distant two-dimensional surface. Just as a hologram contains all the information of a three-dimensional image on a two-dimensional surface, our universe's information might be stored on a vast, distant boundary. If the universe is indeed a quantum computer, it forces us to reconsider everything we thought we knew about reality. Time, space, matter, all could be emergent properties arising from the underlying information processing happening at the quantum level. Our perception of a solid, objective reality might be nothing more than a convincing user interface, a way for us to interact with the vast computational process that underpins our existence. Join us as we dive deeper into this rabbit hole of cosmic proportions. We'll explore the groundbreaking theories of physicists like Seth Lloyd, unravel the mysteries of ER=EPR, and discover how concepts like qubits and tensor networks are helping us to map the universe's computational architecture. This is a journey that will challenge your perception of reality and leave you questioning the very nature of existence itself. In our quest to understand the universe as a quantum computer, we must first grapple with one of the most bizarre phenomena in the quantum world: entanglement. Imagine two particles linked in such a way that they share a single fate, no matter how far apart they may be. Change the state of one, and the other instantly responds, as if connected by an invisible thread. This is the essence of entanglement, a concept so strange that even Einstein called it spooky action at a distance. Entanglement suggests a profound interconnectedness within the universe, a hidden web of relationships that defies our classical intuitions. To grasp the universe as a quantum computer, we need to shift from bits to qubits. In a classical computer, bits are either 0 or 1, like a light switch, but a qubit can be both 0 and 1 simultaneously. Imagine a coin spinning, neither heads nor tails but both. This superposition gives quantum computers immense power, exploring all possibilities at once. The true power of a quantum computer lies in its ability to perform parallel processing on an unprecedented scale. Imagine searching through a maze with a billion different paths. A classical computer would have to explore each path one at a time, a process that could take eons. But a quantum computer could explore all paths simultaneously, finding the correct solution in a fraction of the time. This ability to explore multiple possibilities at once is what gives quantum computers their quantum advantage over classical computers, particularly for certain types of problems. And if the universe itself is a quantum computer, then this parallel processing power could explain how the universe manages to calculate its own evolution, from the smallest subatomic interactions to the largest cosmic structures. Every interaction between particles, every fluctuation in space-time, every burst of energy could be seen as a computation, a complex dance of information unfolding across the cosmic tapestry. The universe wouldn't be limited by the linear progression of time as we experience it, but could explore all possibilities simultaneously, constantly calculating, evolving, and refining its own existence. The idea that the universe is a quantum computer challenges us to reconsider the very nature of reality itself. What we perceive as solid matter might be nothing more than a manifestation of information, a complex pattern emerging from the underlying quantum computations. Just as the pixels on your screen create the illusion of images and videos, the information processed by the universe could create the illusion of space, time, and matter. This concept, known as the holographic principle, suggests that our three-dimensional reality might be a projection of information encoded on a distant two-dimensional surface, much like a hologram. If the universe is indeed a quantum computer, then information would be the fundamental building block of reality, the raw material from which everything else emerges. This shift in perspective from matter to information has profound implications for our understanding of the cosmos. It suggests that the universe isn't just a vast collection of stuff, but a dynamic, self-organizing system governed by the laws of information processing. If the universe is a quantum computer, where is all this information stored? Some physicists believe the answer lies within black holes. Black holes challenge our understanding of information. Classical physics says information is lost forever in black holes, but quantum mechanics says information cannot be destroyed. This creates a paradox. Where does the information go? Some believe black holes store information like cosmic hard drives. Black holes. These enigmatic objects have captivated our imaginations for decades, conjuring images of cosmic abysses from which nothing, not even light, can escape. But what if black holes aren't the cosmic dead ends we once thought they were? What if instead of annihilating information, they hold the key to understanding the universe's computational power? Imagine a black hole, not as a void, but as a cosmic hard drive, its immense gravitational pull compressing information into an incredibly dense and complex form. This seemingly counterintuitive idea arises from the intersection of quantum mechanics and general relativity, two pillars of modern physics that often seem at odds with each other. Einstein's theory of general relativity describes gravity as the curvature of spacetime caused by massive objects like black holes. Quantum mechanics, on the other hand, governs the microscopic world of atoms and particles. Reconciling these two theories is one of the greatest challenges in modern physics, but the study of black holes offers tantalizing clues. Enter the holographic principle, a mind-bending concept that emerges from the study of black holes and their enigmatic properties. Imagine for a moment that our three-dimensional reality, with all its depth and complexity, is nothing more than a projection of information encoded on a distant two-dimensional surface. Just as a hologram can create the illusion of depth and volume from a flat surface, our universe's information might be stored on a vast, distant boundary, perhaps at the edge of the observable universe. This boundary, often referred to as the holographic screen, would hold the blueprint for everything we perceive, from the smallest subatomic particles to the grandest cosmic structures. If the holographic principle holds true, it would mean that space and time, as we experience them, are not fundamental properties of reality, but emergent phenomena. They would be analogous to the texture and color of a holographic image arising from the underlying information encoded on the holographic screen. The holographic principle provides a framework for understanding how information might be stored in a universe governed by quantum mechanics. But black holes present a unique challenge, known as the information paradox. According to classical physics, once something crosses a black hole's event horizon, it's gone forever, its information lost to the universe. However, quantum mechanics tells us that information cannot be destroyed, only transformed. This creates a fundamental conflict. Where does the information go when something falls into a black hole? Does it vanish, violating the laws of quantum mechanics? Or is it preserved in some way, perhaps encoded on the black hole's event horizon? This paradox has puzzled physicists for decades, but the idea of the universe as a quantum computer offers a potential solution. If the universe processes information like a quantum computer, then black holes might not be information sinks after all. Instead, they might act as cosmic processors, encoding and transforming information in ways we are only beginning to comprehend. The implications of the universe as a quantum computer extend far beyond black holes. If information truly lies at the heart of reality, it could revolutionize our understanding of the cosmos and our place within it. The seemingly solid world around us, the fabric of space-time itself, might be nothing more than a sophisticated simulation, a product of the universe's ongoing computation. This paradigm shift, from matter to information, challenges our most fundamental assumptions about the nature of reality. It suggests that the universe isn't just a vast collection of stuff, but a dynamic, self-organizing system governed by the laws of information processing. In this new framework, the universe's evolution, from the Big Bang to the formation of stars and galaxies, to the emergence of life itself, could be seen as a grand cosmic algorithm unfolding, a symphony of information processing that continues to this day. Join us in the next act as we explore the groundbreaking work of physicist Seth Lloyd, who has developed a compelling theory of the universe as a quantum computer, and delve into the mysteries of ER=EPR, a concept that connects entanglement with the fabric of spacetime itself. So far, we've explored the mind-bending concepts of quantum mechanics, black holes, and the holographic principle, all hinting at the universe's potential to be a colossal quantum computer. But how does this cosmic computation actually work? Enter physicist Seth Lloyd, a pioneer in the field of quantum information theory, who has developed a compelling framework for understanding the universe as a self-computing entity. In his view, every particle, every interaction, every fluctuation in space-time can be seen as a computation, a complex dance of information governed by the laws of quantum mechanics. These qubits, entangled across vast cosmic distances, constantly exchange information, perform calculations, and update the state of the universe. Every interaction between particles, from the smallest subatomic collisions to the grand waltz of galaxies, can be seen as a step in this cosmic computation. But how can something as simple as quantum interactions give rise to the incredible complexity we observe in the universe, from the intricate dance of molecules to the emergence of life itself? Lloyd argues that the universe's computational power lies in its ability to process information in parallel, exploring countless possibilities simultaneously. This parallel processing power allows the universe to explore a vast landscape of complexity, from the formation of stars and galaxies to the emergence of life and consciousness. In this view, the universe isn't just calculating its own existence, it's also giving rise to conscious observers like us, who can marvel at its grandeur and ponder its mysteries. If the universe is indeed a quantum computer, it begs the question, can we ever hope to understand its programming language? Can we decipher the cosmic code that governs its operations and unlock the secrets of its existence? The challenges are daunting, to say the least, It's estimated that the universe could have performed more calculations in its lifetime than there are atoms in the observable universe. Furthermore, our understanding of quantum mechanics is still in its infancy, and we're only beginning to grasp the potential and limitations of quantum computation. Just as we've cracked the codes of DNA and the atom, the quest to understand the universe as a quantum computer could lead to profound breakthroughs in our understanding of reality, potentially revolutionizing fields like physics, computer science, and even philosophy. Some physicists, pushing the boundaries of this mind-boggling concept even further, speculate that the universe might not just be a static computer program, but a dynamic self-learning system. Just as artificial intelligence algorithms can learn and adapt based on new information, the universe itself might be constantly refining its own code, evolving its computational strategies over billions of years. This raises profound questions about the nature of free will, determinism, and the role of consciousness in shaping the universe's destiny. Is the universe conscious of its own existence? Is it striving towards some ultimate goal? Or is it simply a vast, indifferent machine, blindly processing information according to the laws of physics? Join us in the next act as we delve deeper into the mysteries of the universe's computational tapestry, exploring the mind-bending concept of ER=EPR, and its implications for the interconnectedness of spacetime and information. Our journey into the heart of the cosmic computer has led us to some of the most bizarre and profound concepts in physics: quantum entanglement, black holes, and the holographic principle. Now, we arrive at a crossroads, a point where these seemingly disparate threads begin to weave together into a tapestry of interconnectedness that could redefine our understanding of reality itself. ER=EPR. This deceptively simple equation, first proposed by physicist Juan Maldacena, and later refined by Leonard Susskind and others, represents a profound link between two seemingly unrelated concepts: entanglement and wormholes. On one side of the equation we have ER, representing Einstein-Rosen bridges, more commonly known as wormholes, theoretical tunnels that could connect distant points in space-time. What ER=EPR suggests is that these two phenomena, once thought to be entirely separate, might actually be two sides of the same coin. Wormholes have long captured the imagination of science fiction writers and armchair physicists alike, offering the tantalizing possibility of faster-than-light travel and journeys to distant corners of the universe. However, wormholes remain theoretical constructs, and their existence has yet to be confirmed by observation. Wormholes, in essence, would be extreme distortions of spacetime, creating tunnels that could connect two distant points, potentially allowing for shortcuts through the cosmos. However, creating and stabilizing a wormhole would require exotic forms of matter with negative energy density, something that has never been observed. If ER=EPR is correct, then entanglement isn't just a strange quirk of the quantum world, but a fundamental force shaping the very fabric of spacetime. Imagine a universe where every particle is entangled with countless others, forming a vast, interconnected web of quantum correlations. These entanglements, according to ER=EPR, could be creating microscopic wormholes, stitching the fabric of spacetime together at the quantum level. This interconnectedness could explain how information is shared and processed across vast cosmic distances, allowing the universe to function as a unified computational system. It's a tapestry of interconnectedness, a symphony of quantum correlations orchestrated by the laws of physics. If ER=EPR holds true, it has profound implications for our understanding of spacetime itself. Instead of being a fundamental aspect of reality, spacetime might be an emergent phenomenon, a macroscopic illusion woven from the underlying tapestry of quantum entanglement. Just as the solidity of a table emerges from the interactions of countless atoms, the fabric of spacetime might emerge from the intricate dance of quantum entanglement across vast cosmic distances. The seemingly smooth continuity of space and time could be a grand illusion, a convenient approximation that breaks down at the quantum level. Join us in the next act as we delve into the tools and techniques that physicists are using to map the universe's computational architecture, exploring the concepts of qubits, tensor networks, and the quest to simulate the universe itself. We've journeyed deep into the theoretical heart of the universe, exploring the possibility that it operates as a colossal quantum computer. But if the universe is indeed computing, what is the language it uses? What are the fundamental building blocks of this cosmic code? The answer might lie in the enigmatic realm of qubits. Unlike classical bits, which can only be either a 0 or a 1, qubits can exist in a superposition of states, simultaneously embodying both possibilities and everything in between. Imagine a coin spinning in the air, neither heads nor tails, but existing in a blurry state of both possibilities at once. This ability to inhabit multiple states simultaneously is what gives quantum computers their immense computational power. If the universe operates on the principles of quantum computation, then qubits could be the fundamental units of information, the language in which the cosmos writes its own story. But how do we go from individual qubits to the vast interconnected web of information that would be required to represent the entire universe? This is where the concept of tensor networks comes into play, providing a powerful mathematical framework for understanding and potentially mapping the complex relationships within a quantum system. Tensor networks provide the mathematical tools to describe these connections, allowing physicists to model how information flows through the network and how different parts of the system influence each other. By studying the structure of these networks, physicists might uncover hidden patterns and relationships within the universe, revealing the underlying code that governs its evolution. If the universe is indeed a quantum computer, it begs the question, can we create our own smaller-scale simulations of reality using quantum computers here on Earth? Could we, in essence, build a universe in a box, a digital sandbox where we can manipulate the laws of physics and observe the emergence of complex phenomena? These simulations are providing valuable insights into the behavior of matter at the atomic and subatomic levels, helping us to better understand phenomena like superconductivity, quantum entanglement, and even the early universe. These simulations could revolutionize our understanding of everything from the formation of black holes to the emergence of life itself, offering a glimpse into the universe's inner workings that would be impossible to obtain through observation alone. The idea of the universe as a quantum computer is still in its infancy, a tantalizing hypothesis that has yet to be definitively proven. But the very act of exploring this concept is pushing the boundaries of physics, forcing us to confront profound questions about the nature of reality, information, and our place in the cosmic order. The journey to decode the universe has only just begun, and the discoveries that await us promise to be nothing short of revolutionary. Our journey through the cosmos has taken us to the very edge of human understanding, challenging our perceptions of reality and revealing a universe far stranger and more wondrous than we ever imagined. The idea that the universe might be a colossal quantum computer is a profound one, suggesting that information, not matter, is the fundamental building block of existence. It paints a picture of a cosmos where everything is interconnected, where entanglement weaves the fabric of space-time, and where the laws of physics are the rules governing a grand cosmic computation. We become not just passive observers but active participants in the cosmic computation, our every thought, action, and interaction contributing to the universe's ongoing evolution. The quest to understand the universe as a quantum computer is still in its infancy, a frontier of knowledge ripe with tantalizing possibilities and profound implications. As we delve deeper into the quantum realm, develop more powerful quantum computers, and refine our models of the universe, we can expect to encounter even more mind-boggling concepts and paradigm-shifting discoveries. But within these challenges lies the greatest reward of all, the expansion of human knowledge and the realization that the universe is far more complex, interconnected, and awe-inspiring than we ever dared to imagine. The journey to understand the universe as a quantum computer is a journey into the very heart of existence itself, a quest that promises to illuminate not only the nature of the cosmos, but also the very essence of who we are.